My name's Jeff Galvin, and I am the CEO of a company called American Gene Technologies. And my background is kind of unusual because I started off as a computer nerd, and we're talking back in the 70s when I was in junior high school. So I'm a million years old. Don't bother to calculate it. It's, I need to be carbon dated. What happened is that I really fell in love with computers in junior high school. This was in the really early days when computers filled, huge rooms or whole floors of buildings. And mini computers were just coming on the scene. There were no microcomputers. There were no cell phones, obviously. But I saw in computers something that was going to alleviate a lot of people from suffering, I thought, because I thought the most, the thing that caused me the most pain is doing all these boring rote activities. And I could see immediately that computers were going to remove all of the work of adding numbers, formatting documents. And I was living in the Boston area, and so I used to wander around on campus at MIT, and I saw robotics and sensor technology. And I realized, okay, these things will eventually drive our cars, fly our planes, build everything for us. And so I saw this amazing future where this new technology was going to lift up humankind. That was what was exciting for me. I was not really a computer scientist, but I was really a computer nerd because I was in love with them. So I did win a bunch of programming contests and things like that. Eventually, wandering around MIT, they recruited me to teach a weekend class to high school students and college students on beginning computer science, believe it or not, at MIT. So at age 15, I was teaching there. At age 17, I got admitted to Harvard. In my sophomore year, I started teaching there undergraduate classes. So I was responsible for all of the teaching fellows, which is teaching assistants, for a 1,200 person class that was beginning computer science for non-computer scientists. And why was that just perfect for me? Because I got to share my love of this technology with my fellow students. And what I could tell them is that I don't care what you're going into, you will either program a computer, you will work with a programmer, or you will use a computer and it will enhance your career no matter what it is you plan to do. And that absolutely turned out to be true. So fast forward past that, I get recruited to Silicon Valley. I work at Hewlett Packard and Apple, and then Apple really lit the entrepreneurial fire in my belly. It was the first company that I met that actually understood computers the way that I did. These should be in everybody's hands. They understood that the graphic user interface was a key component to having computers broadly adopted by everyone, right? And this was not something that was generally accepted. As a matter of fact, there was a story that I heard from the Apple executives, and we used to just, go out for beers back in those days, in early 80s. I mean, I knew Mark Markula, I saw Steve Jobs around all the time, Steve Wozniak, people you haven't heard of, Gene Carter, Floyd Kwame, these were all the executives of Apple back when we were only a billion-dollar company. But it was an amazing time to be at Apple, and they got it. They were passionate. They had the fire in the belly to, take a better idea and bring it out to the world and revolutionize computing. So I loved that environment, and I went on and did a bunch of startups in software, internet, IT, things like that. Enough of them hit. There I am, 42 years old in Silicon Valley, retired. I look at my bank account, I don't have to work anymore. And I thought, yeah, that was always my dream. Retire early. Sounds good, doesn't it? I bought a house in Hawaii across the street from the beach, and my life was flying back and forth between San Carlos, where I had my home in Silicon Valley. And if it would get too cold in Silicon Valley, I'd just hop a plane and I'd be on the beach 3 hours later, 3 hours clock time later, 5 hours. I could be on the beach basically with 3 hours in clock time. And it was a great life for about 5 years. And then, believe it or not, it gets boring. When you have the energy to work, when you have a mind that hasn't slowed down yet, you want stimulation for it. You want to feed it something. And so I thought I'll just dabble in technology again. And so the natural thing to do would be to invest some money in a local Bay Area startup, mentor another entrepreneur, join a board, something like that. But as soon as people find out you have money, you start getting business plans from all over the place. And I get one from the National Institutes of Health. It's from a lab out there, and one of the postdocs is interested in starting a company in what's called DNA microchips. You guys probably know about these things. I don't even know that much anymore. I don't know what the progress has been, but it seemed like an interesting idea, and I could see that this could be something that would be very important in the future of medicine, because I sort of had this idea of personalized medicine based on your genetics. And the idea of being able to just read a lot of your gene expression on a chip real quickly seemed like a great idea. So I went out to see it. And that guy introduced me to somebody named Roscoe Brady, who showed me viral vectors. Okay, show of hands here. How many people know all about viral vectors already? Holy cow, 0. That's amazing to me. Oh, you're gonna love this talk, okay? Because there is a revolution going on right now that is going to completely change the entire future of pharmaceuticals, and it's going to bring cures to diseases that can't even be treated right now. You know, I was alluding earlier in the discussion that, you know, you guys don't have to worry about cancer. You know, all you need to do is avoid it for another 10 years, which I think is fairly easy when you're this young. Or, you know, somehow treat it and knock it back. But, you know, we're working on things at AGT right now, where if you were to get a metastatic breast cancer, okay, now this is not done yet. It's not tested in humans, but we have mouse data that shows this to be very, very promising. And one thing I can absolutely say to you is that if we don't accomplish this, somebody else will, all right? Because this is just what nature is revealing to us in the use of viral vectors, all these opportunities to go in and to attack the root drivers of disease, or to stimulate your immune system in a way that, you know, was impossible before, to eradicate a pathogen in your body, and that pathogen could even be cancer. And so we have something where in a mouse, in advanced stages of human cancer, we go ahead and take a syringe and we inject some virus into one tumor, and all the tumors disappear. And they disappear because we activate a T cell subset called gamma delta T cells, and they start their natural surveillance of epithelial malignancy. Epithelial malignancy is the start of breast cancer, prostate, liver, kidney, ovarian, pancreatic, head and neck, skin cancers, lung. All of these deadly cancers start as small malignancy in epithelial layers of organs. And you have a T cell subset, which is really great at finding these small malignancies and eliminating them before they can turn into something serious. And probably while we're on this call, one of your gamma delta T cells has eliminated a malignancy. And they are so effective that 2 out of 3 people will never get a deadly cancer tumor of the epithelial type. That's amazing, right? But 1 out of 3 people will. And what do you get if you find out you have a malignant tumor, let's say in your breast or in your lung, or, you know, in your prostate? If I only see women with their screens on now, but I think I see some male names down the list here. So, you know, we all have to worry about one of these things, right? You know, women are more conscious of breast cancer. That's more common in women. Men can get breast cancer, by the way. Women can't get prostate cancer, thank goodness, because you just don't have prostates. But you have to worry about ovarian cancer. We all have to worry about colon cancer, right? But what do you get when you find out you have a malignant, solid cancer in some part of your body? Well, you get surgery followed by radiation, followed by chemotherapy, right? Sometimes 5 years of hormone treatment just to make sure, you know, that you minimize the chances of it coming back. So what's the theory behind this? Well, you got cancer, something growing that shouldn't be there. Cut it out. Makes sense. Best thing we got. Then you think, well, what if we missed a little bit of it? Maybe we better irradiate it. And you know, so we're beaming cancer-causing radiation through your body, but because we do it from so many angles, the only part of your body that's getting enough radiation to kill cells is the part we're targeting in the middle, like the hub of a wheel. You know, it's, if you can imagine, that's, I used to work in oncology clinics that used radiotherapy like this, you know, it's kind of scary. But it's the best thing we've got right now for that type of surgery. And then what if some of it spread to some part of your body that we didn't detect? What's the next thing we do? We poison you. That's what a chemotherapeutic is. It's a poison where it goes a little bit, it gets eaten up or uptaken a little bit more by the cancer cells, usually because they're dividing more rapidly. And so we can give you a dose where hopefully the cancer cells get enough of it that they can't recover, but the overall dose isn't so high that you don't recover, right? Because people can die in chemotherapy, right? You don't think about that, but it's like an art. How do we give you just enough poison that we're sort of walking this razor's edge between, you know, you dying and, you know, getting all the cancer? We go too low, we don't get all the cancer. We go too high and we kill you. It's crazy, right? But I think that within your lifetime, you're going to see radiation and chemotherapy go the way of bloodletting and leeches. And I'm already seeing the light at the end of the tunnel at American Gene Technologies. You can find out all the details about this on the website, but let me describe it real quickly for you, how it works. As a matter of fact, I have a slide that I want to share with you guys. Let me just go ahead and find the specific slide here. There it is. Ah, good. It's ready to go. So what I need to do is I need to go back to this and share my screen with you. Okay, are you seeing a slide on the screen that's blank? Yeah, okay, thank you. All right, so first step is you get a solid tumor, right? And why do you get a solid tumor? So my guess is that the older you get, the more you age, the more accrued stress on your cells, the more of them sort of either age out or stress out. And when a cell dies, it could go one of two ways. It could essentially just perish and be dissolved by your macrophages and carried out of your body, or it may decide for some weird reason to try to save its own life. And there's this whole set of what are called oncogenes in your body that will allow this cell to rapidly multiply. Now, you know, this must have had some benefit in, you know, in the original evolution of humankind, because it's all there in your genes. It hasn't evolved out of it yet. So cancer probably has some role in our evolution. I don't know what that is, but I do know that if you live long enough, you have a higher chance of getting a solid tumor. And part of that may be this, sort of stressing out of the cells over time. And the other thing is the older you get, and also from stress, your immune system may go down. So this surveillance you have for these epithelial malignancies is being reduced over time as well. So you go along for a while, and then somehow a few cells don't get caught fast enough. It turns into 6 cells, 12 cells, whatever. It gets ahead of the surveillance system that can eliminate 1 or 2 cells at a time, and it starts blowing up like a balloon. That is your solid tumor, right? And by stress, I mean, look, we all go outside, we all get radiation, we all eat, we all get chemicals, we all get, all sorts of things that are stressing out our cells. Okay, so I told you we're gonna, a normal tumor now would be surgery, radiation, and chemotherapy. So here's what our alternative is. We take a viral vector. So a viral vector is just a virus that has been modified to carry a gene that can affect the cell that the virus infects. And I'm gonna stop this for a second so I can just quickly go over viral vectors. Am I back again, full screen somewhat? Okay, so what are viral vectors? Well, you know that your body in your cells is run with DNA, right? DNA contains all the instructions for every single one of your cells. And even though your cells are all different, they all have the same DNA, or roughly the same DNA. And it turns out that each one of your cells has a manager in the nucleus that knows what part of the DNA applies to that cell, right? But it turns out, we found out in the 80s, that you can drop what are called plasmids, genetic coding, into a vat of cultured cells. You can shock those cells so that it uptakes that genetic coding. And it can be for a gene that is codes for something that that cell has never made before, right? Like we can culture up kidney cells in a big vat, like a giant soup vat or soup cooker. And then we can drop in plasmids that code for human insulin. Now, kidney cells don't normally make human insulin, but if we shock the cells, they will uptake that insulin command, and voila, they start secreting insulin. Now, that's really useful because it got everybody off of bovine insulin who needed it for diabetes, right? So that was the birth of Genentech. How many people here have heard of Genentech? You must at least ride by it on the highway from time to time. So Genentech started in these purified proteins like human insulin, and then it went into monoclonal antibodies, and it ended up growing to be worth $80 billion, and it was sold to Roche, a giant pharmaceutical company. All right, but they were the first ones to really commercialize this idea of making important enzymes for your body in these cultured cells. So the next thing that was discovered was in the 90s when they realized, well, viruses have been bringing genetic constructs into cells for 1.5 billion years. Could we somehow repurpose viruses as a delivery mechanism to bring these genetic constructs into cells? Turned out they could. They found a way where you can crack open any virus. I'm talking about any virus. What's a really scary virus? HIV, right? That's a scary one. COVID's a virus too. You remember how fast COVID got sequenced? They could crack it open and they could find the sequence of all of the genetic instructions inside COVID very, very quickly, right? This all comes from the Human Genome Project, where the first genome cost $3 billion to sequence, right? Now it's under $1,000 for a full sequence. I don't even know what the price is, but it's dropping like a rock. Okay, but it all comes from the fact that we have these things called enzyme restriction. Anybody here have heard of that before? That allows you to go ahead and break DNA strands in specific places. And we can actually crack open viruses and we can find all of the information that we need about how that virus is constructed from its genetic sequence. Because the genetic sequence is just a description of how to build a viral envelope, how to build a virus contents, and a packaging signal that pulls them together. That's what a virus is. But now that we can crack it open, we can get rid of the viral DNA. So let's say we're cracking open HIV. We can scoop out AIDS, throw it away. What do we have left? An empty stealth bomber that can deliver any payload we want. This industry has progressed so far that you can get on your computer and you can order any human gene you want off the internet. Put down your credit card, it'll come by FedEx the next day as a plasmid. And if you have enzyme restriction capability and things like that, you can slice it out of the plasmid. You can go ahead and put it into a viral vector. You can package that viral vector into a viral shell. And then you can take that virus and you can infect a cell. It will install, if it's HIV, remember HIV installs new genes inside your DNA. So if it's an HIV shell and an HIV vector, it'll install that gene permanently in the cell that it infects, right? Let me ask you this. What's the difference between a virus on your computer and an update? One's benevolent and one's malevolent. And that's what we're doing, is we're converting viruses into updates for the human computer, the human cell, right? Why do I think the human cell's like a computer? Because it operates off of a list of instructions called genes They're not coded in zeros and ones like your cell phone, but they're coded in ACTG, right? The nucleotides of your DNA. And the sequence of the ACTGs is the command. The command goes into the machine, and the machine pumps out something in response to the command. And really, the human cell makes a digital computer look like pretty crude, pretty barbaric. You know, the human cell, it literally can manufacture and work in all the materials it's made out of. There's even a command in the cell that says, make a copy of me. Try to make your digital computer do that, right? That's the idea, is that, you know, there's a lot to discover in terms of how all the capabilities of this organic computer. But with what we know now and our ability now to take viruses and install new commands in people right in the clinic, right? I can take, you know, any of you, and I can inject a virus into your liver that will install a gene that maybe you're missing in your liver, and it could cure a what? A monogenic loss of function disorder, an inherited disorder in your liver, right? Because there's 7,000 diseases out there that are no more than you were just born with a broken gene. They can range from lactose intolerance all the way up through spinal muscular atrophy. Lactose intolerance, okay, you avoid milk products, or you take lactase, you know, before you eat anything milk related. Born with spinal muscular atrophy, those babies are dead by age 4 because they never form a normal spine, normal muscles around the spine, because they're missing one protein in their body. They're missing the coding for one thing in their spine. And as a result, they end up not ever being able to keep their head up straight, roll over, sit up, move normally, and eventually they can't even breathe on their own. They end up dying in ventilators by age 4. One gene. Well, we can order the gene off the internet. We can go ahead and put it in a viral vector. We can test it in a cell model and see if it installs and expresses at therapeutic levels. We're on our way to curing that disease. And we have one of those, you know, it's a cure for something called phenylketonuria. We're on our way to curing that. But there's way more that you can do with these viral vectors, right? And cells. You could actually improve a cell's capability of doing its job. Okay, so what's an example of that? Well, why do some people get HIV? It's because you have these HIV T cells in your body that are supposed to fight it so that it can't get in. That HIV viron is more fragile than a cold viron. It lasts less time in your body than a cold viron does. It's easy to kill. But the problem is it's evolved this capability that when that first T cell comes over to try to kill it, it grabs onto the T cell and it actually can merge with the T cell and install its DNA into the T cell permanently. So the sentinel T cell that was in your body that has evolved to protect you from HIV is the first one that arrives at the pathogen, the first one to become infected, and becomes the beachhead of the infection. It actually goes back to your lymph nodes. It replicates itself. Since when cells divide, they replicate their DNA. Now you have 2 infected cells or 10 infected cells, right? It even infects your lymph nodes. Now you have a chronic viral infection in your body. And after 90 days, every single one of your HIV T cells is infected and killed. And then it could take 5 years before you even know you have HIV, because it could take that long to randomly collide with T cells that aren't looking for it. Like a cold T cell couldn't care less about a HIV viron. You got to have enough virons in your body that the cold T cells are just randomly colliding. And then it gets a grip on a T cell, a cold T cell, and infects that one. That one makes HIV for a little while, and then it dies. Once you lose all your cold T cells, well, you get a cold that you can't kick that turns into pneumonia, and a lot of people that find out that they have HIV that way. Okay, so it all comes down to that initial infection, right? The T cell isn't effective at killing the viron because the viron can grab the T cell and infect it. Did you know that there are people in Northern Europe who are immune to most common strains of HIV? They're born immune. The way that they're born immune is that they have a rare genetic defect where they have no protein called chemokine receptor number 5 on their T cells. All right. Now, what does that do to their T cells, right? If you are born with a genetic defect where you're not making lactase, you're lactose intolerant, right? And so if you're missing CCR5, the positive thing is it turns out that the way that HIV grabs onto the T cell, it needs 2 handles. One is CD4. Every T cell has CD4. Every CD4 positive T cell has CD4. The other one is CCR5. If it can't get a hold of that handle, it can't bind tightly enough to the membrane, and it can't infect the cell. So these people are effectively immune to the virus. So what's the downside of not having CCR5? Well, it turns out CCR5 is useful for crawling through tissue. So those people have higher rates of fungal and bacterial skin infections that are harder for them to kick. But I mean, as a typical college student, would you trade having to put the occasional fungal cream on or antibiotic on your skin to be immune to HIV? I think you would, right? I know when I was in college in the 80s, I would have done it in a heartbeat, right? It was really scary back then. We knew nothing about it. But the question then becomes, well, if these people are immune to HIV, is there some way to give that immunity to somebody who already has HIV? Or give it even that immunity to somebody who hasn't had HIV yet? Because all of us have HIV T cells, but most of us have HIV T cells with CCR5 on them. So, well, turns out we can go ahead and infect a T cell with a gene that produces what's called an interrupting RNA, an antisense strand. And what that will do is we can tailor that antisense strand to bind to the message from CCR5, the CCR5 gene. And by knocking out the message, it's effectively shutting off the gene. When you shut off the gene for a protein that's on the surface of the cell, the protein eventually falls off and the cell becomes CCR5 negative. So we could give that superpower to anybody. And the way that we do it was with an autologous cell therapy. We improve your existing T cells by stripping CCR5. Now, the most common strains of HIV can't get in. And have you guys heard, how many people here have heard of CAR T? Wow, you're so young and so naive, and you don't have to think about these things. But CAR T is a recent cure for acute myeloid leukemia and acute lymphoid leukemia. Thank goodness nobody on the call has heard of these things because you haven't needed it. Hopefully you never heard of spinal muscular atrophy or phenylketonuria, right? But one day you may encounter any of these things, either personally or somebody that you love. Okay, so if we can improve your HIV T cells so that they look more like these people that are naturally immune in Northern Europe, then you no longer have to worry about HIV. What about somebody who has HIV already? Well, they did an experiment because it's common that people who have HIV get leukemias and lymphomas, and they're incurable. The only way you can cure a lymphoma or a leukemia once it spreads so completely throughout your body and it won't get knocked back by chemotherapy or radiation anymore, they do what's called a bone marrow transplant. Hands for how many people know what a bone marrow transplant is? Essentially, they irradiate your whole body. They destroy your entire immune system and your bone marrow, which is where your immune system comes out of. So your red blood cells, your immune cells, all these things come from your bone marrow. So then they find a donor who's got bone marrow that doesn't have leukemia, and they put a sample of it in your bones, it regrows. And then your immune system reemerges, a normal immune system, but it's not your immune system that had leukemia anymore. It's that other guy's or that other gal's immune system, right? So some smart physician, researcher in Berlin gets this HIV positive patient who's got an incurable leukemia. And so the only hope for this patient is a bone marrow transplant. And the doctor thinks, what if we transplanted that guy over there's bone marrow who's immune to HIV to this patient? What would happen if he suddenly had T cells that could actually eliminate HIV, that couldn't get it reinfected? Well, long story short, that guy was functionally cured. We sometimes refer to him as the Berlin patient. His name was Timothy Ray Brown. He actually just passed away a month ago. He lived for almost 20 years, functionally cured. He no longer needed daily pills to suppress his virus. His immune system did it naturally. Now, does that mean we have the cure for HIV? Well, sort of. The only problem with bone marrow transplants is 6 out of 10 people who get a bone marrow transplant die from the trauma of that bone marrow transplant. It is, you live for a certain period of time with no immune system, which means the slightest pathogen will kill you, right? You're like, have you heard of bubble boy disease? Kids that are born without an immune system, they live inside plastic their whole life long. And if anything gets in that plastic, like a bacteria or a virus, lights out, right? By the way, cured. That disease is now cured, because it turns out by taking bone marrow, it's missing one protein. That's why they're born without an immune system. They pull out some bone marrow, they infect it with a virus that's carrying that gene that they're missing. They put it back into the kid, and voila, he gets a normal immune system out of the bubble. Tremendous, isn't it? That's the power of gene and cell therapy. That's how powerful your body is. That's how amazing your cells are. That's how amazing this computer that we were born with is. That the human cell. Okay, so I talked about, this whole class of basically improving cells with these viral vectors. And that's what our HIV cure is. So I'm jumping all over the place, and I apologize for this, but I'm going to bring up the slide, and I'm going to finish out my cancer story. All right, and then I'll finish out the HIV story if we have time. Because cancer is something that I think anybody can identify with, right? We all know somebody that's had cancer, or we all are conscious that cancer is out there as a threat. So you get a tumor, and your gamma delta T cells, which are 3 to 5% of your circulating T cells, that are highly effective at clearing small malignancies, there's too much surface area. They can't get to all of it, and it just keeps growing and growing and growing beyond these gamma delta T cells' ability to eat it away. All right, well, what we can do is we can just put a small dose into the tumor of a virus that causes the cancer to overexpress a protein, a stimulatory small molecule, basically a small molecule that is a byproduct of rapid cellular division. That is what those gamma delta T cells are attracted to. So it's like we're either lighting up the tumor for these gamma delta T cells, or imagine that we're putting a perfume in this solid tumor that all of these gamma delta T cells can smell and are attracted to. Now, what this does is it causes almost a vaccine effect. These gamma delta T cells will be attracted to that tumor where there's a high concentration of this molecule that they're looking for, that is their indicator of cancer or of rapid division. But they don't just kill everything in sight. That's not how gamma delta T cells work. They're attracted by a T cell receptor, but they decide to become cytotoxic with an NK receptor. An NK receptor matches a set of stress molecules on a malignant cell. It's highly specific. We call it exquisitely specific. And when it senses that in that area, it finds a cell that has those stress molecules, it kills the cell. And it's a great killer of the cell. Well, with all of these gamma delta T cells coming in and seeing this very, very high level of this small molecule that's indicating rapid division, it has a vaccine effect on these gamma delta T cells. They are attracted, like I told you. They're trained. They are proliferated. These things will actually increase in numbers, and then they're activated. The activated part is the important part, because in an activated state, they can eat at 300 to 600 times the normal rate. And that's enough to chew away that tumor. So the gamma delta T cells come in, like this gray thing here, they proliferate and they activate. They turn on that tumor and they blow it apart. Now remember, they don't attack the cells that are producing the stimulatory small molecules. That's represented by the red cells in this diagram. We don't have to get every cell in the tumor. We just have to get about 20% of them, so we get a high enough concentration of this molecule called IPP that we start this reaction. So now you've got these gamma delta T cells that are in this hungry killer state. Of course, they kill the primary tumor, but guess what? They're constantly circulating around your body during this whole process. They find the metastases without you having to treat them. They find secondary tumors without treatment. So they don't just clear the primary tumor. In the process of clearing the primary tumor, they're clearing every tumor in your body. And that includes even unrelated tumors, because they don't know the difference between breast cancer and lung cancer. So if we treat you for lung cancer, and it turns out you have some breast cancer that you don't even know about, it's going to mop that up. So this is very much like rewinding your cancer clock. You show up at the oncologist and you've got a detectable tumor somewhere. If they can get to it with a needle, either arthroscopically or with a syringe, and think about in the breast, a syringe is easy. In a prostate, a syringe is easy. And they just put some viral vector into that primary tumor. No surgery, no radiation, no chemotherapy. An outpatient visit for that injection. Come back 6 weeks later to be imaged, and you've rewound your cancer clock by 5 to 10 years. You might need it again, but you can just take the same treatment again. So this is why I think that at worst case, cancer will become a chronic disease. If you're cancer prone, you may end up in the doctor's office every 5 to 10 years needing a shot. Sounds a lot better than the alternative, right? I mean, this is really something, because it means that even people that are BRCA1 or BRCA2 negative, you know what that means to be BRCA1 or BRCA2 negative? It means that a cleanup mechanism in the breast is missing. It's like gamma delta T cells. It helps to knock back breast cancer, which is why when you have normal BRCA1 and BRCA2, you generally have only a 1/3 chance of getting cancer, just like everybody else. But when you don't have that, you have an increased chance. But that same cancer is also fought by these gamma delta T cells. So we wouldn't have to think of that as, you know, a risky condition any longer. We just wait. You know, we just keep monitoring, and you get a lesion, we treat it. Every time you have a solid tumor, it's really an opportunity to give your body a epithelial cancer flush. Amazing, huh? Now, I'll tell you, this is preclinical, but we have a 1,000 mouse study where 85% of the mice who have multiple tumors of multiple types, they're all human xenograft cancers. So we might grow human liver cancer on one side of the mouse. We might put human breast cancer on the other side of the mouse. Then we treat one of the tumors, almost nothing happens. But then you take human gamma delta T cells, put it into the peritoneum of the mouse, nowhere near the lesions, and all the lesions disappear. 85% of the mice come back with 0 cancer in their body. Now remember, in the human, it should work even better. You already have gamma delta T cells. You can make more if you need them. So I think this is going to translate beautifully. So I believe, and our collaborators at the Stanford Medical School, a guy named Dean Felsher, you can see him on our website. He's our principal investigator out there and our consultant. He's been with us for over 5 years, really gung-ho on this. I think we'll prove it in liver cancer in 2022 at Stanford. Okay, so now let me back up to HIV. How are we doing for time, by the way? Looks like we have 13 minutes according to my clock. By the way, I don't have a hard deadline. I don't know whether you guys have to all cut out at that point or not, but I'll keep talking and answering questions in the meantime. Let me see here. Let me find the other diagram.
I have a question about this slide, actually.
Okay.
What was that?
Are you still seeing the slide now? Are you seeing another slide? Okay, I think I see nodding. So this is how we do HIV. We pull a 400, in step number 1 here, we pull a 400 milliliter Leukopak. So somebody who has HIV, they have no HIV T cells. But when they get on antiretroviral therapy for 1 to 3 years, they get all their T cells back. Now, why do we know that you get your normal T cells back? Well, if you weren't able to fight colds before, once you suppress the virus, suddenly you can fight colds and the flu and whatever again. That's because these T cells that you're missing reemerge from the bone marrow. So once we suppress the virus, you don't just get back your cold T cells and your flu T cells, you get your HIV T cells back as well. The only problem is that they're no better than your original ones that let the virus in the first place. So if you stop suppressing the virus, those T cells will just get infected and you'll start the infection cycle all over again. But instead what we do is we draw a 400 milliliter Leukopak. It's like a blood donation, but it's a filtration where we pull out blood, we filter T cells, and we push back in the rest of your blood. So volume-wise, you don't change much, right? But we have a highly concentrated mix of T cells. And in there, we can get a very small number of HIV-specific CD4 helper T cells. Why CD4 helper T cells? Those are the ones that are the conductors of the immune orchestra. It's your HIV CD4 T cells that cause a CD8 response and an antibody response to HIV. But once HIV attacks those CD4 T cells and eliminates them, then you lose the rest of your immune protection. And finally, an HIV strain will come out and infect your whole body. Okay, so if we can put HIV CD4 positive T cells back in there that actually can fight HIV, they can maintain the whole orchestra. They can maintain the whole immune cascade, and you will be naturally immune. Okay, so we get 400 milliliter Leukopak. We put it in an automated benchtop unit. This is called a Miltenyi Prodigy, but we can do it on other types of benchtop units. It doesn't need a clean room. Costs $250,000, which is not expensive for a hospital or clinic. So they hang the blood on there, and they put a bunch of reagents in there that include our viral vector that's going to make the modification to the T cells, some other reagents that are used for stimulating HIV T cells and making them grow, and voila. You press a button, and the machine automatically stimulates the all of the T cells in there so that the HIV T cells proliferate in the mix. So now we have a few more T cells. It's still a very, very low percentage, like 0.001%. But by stimulating them, we could raise it to 0.005%. Then we go ahead and we do a T cell depletion. So we end up ridding the whole sample of all the T cells that are unrelated to HIV. Now, why would we do that? It's only your HIV T cells that can fight HIV. It's the only ones that are important to keep healthy. Viral vector is super expensive. If we treat all of your T cells, number one, we're going to spend a lot of money on viral vector unnecessarily. So it means the treatment's going to be more expensive. And the other thing is we're going to be creating that side effect that I told you about, right? If your bacteria T cells and your fungal T cells are modified, they won't be as effective. So why modify them? Okay. So then we do the transduction. We dump the virus into the mix, and we're getting 95% of the cells are converted to immune to HIV. Then we do a culture step where we grow them up to 1 billion cells. Any immunologists in the group that know why we chose 1 billion as the number? I'll tell you. The reason is because when you clear a viral infection, you normally have about 100 million CD4 positive T cells that are disease specific. So we thought 1 billion is 10 times what you need. That ought to be enough to overwhelm your HIV infection, right? And then we go ahead and we have to do some release testing. That's to make sure that there's no contaminants in this blood product that we made. But assuming there's no contaminants, last step is we reinfuse it. So when we reinfuse it back into the patient, the cells need about a week to engraft. That just means to settle down, because the infusion process will damage some cells, and you want them to have time to recover. You could lose some cells in that as well, but you'll probably still have at least 500 million of these, 5 times what you need to clear the virus. Then you throw away your meds and you're immune for life. So an HIV positive person can control their own viremia at a level where they are what is called functionally cured. You can think of functional as meaning as good as. They can never progress to AIDS, they can never infect another person, and even better, they can never be reinfected, and they don't need any special medication. I don't know if anybody in here knows anybody that's infected with HIV, but they take a daily pill normally to suppress the virus that is a chemotherapeutic that has all sorts of side effects. The daily side effects, you can just watch the Biktarvy ads on TV, are nausea, diarrhea, and fatigue. So nobody feels 100% that has to take that poison every day. But that poison is necessary, a mild chemotherapeutic, to prevent the virus from moving across the blood to other cells and to suppress the virus long term and prevent AIDS and prevent transmission. But long term, they get early aging, bone density issues, osteoporosis, brittle bones, liver, kidney, heart disease, and extra cancers. Did you know that the average HIV infected individual costs $50,000 to $100,000 per year in doctor's visits? Not the medication that they're taking only costs $20,000 to $30,000, but the side effects can cost another $50,000 to $80,000 a year to treat. So they're in and out of the doctors all the time. So a cure for this is worth a lot of money. The lifetime cost of maintaining that patient could be several $1 million. And this process that I just showed you is about $100,000 to run. That means that Gilead could charge $500,000 for it, and they could save insurance companies tons of money, and they could improve the lives of these patients, would be living normal lives and also not being in the closet. You may know somebody with HIV. They can't tell you about it. You'd be scared of them. It's a natural reaction, right? You don't need to be scared of them. The reality is 1 in 300 adults in the United States is HIV positive. It's crazy. It's an epidemic. But that's the kind of social stigma that they endure. They have a hard time getting a doctor. They have a hard time getting a dentist. If they're open about any of these conditions on the admission form, which they have to be, some doctors won't even treat them. So, this is really important that we move them from HIV positive taking suppressive therapy to functionally cured, where they are normal or even super normal. They literally don't even have to worry about getting HIV again, something that we have to worry about as normal people. So, that's a very important thing. Is it worth $500,000? Yeah, that's already worth $500,000. The insurance companies will pay for it. But also think about the benefit to society. Did you know that there's 30 to 50,000 new cases of HIV every year? It's an epidemic. Polio is only 60,000 cases a year at its peak. So this is really something that is worthwhile to get rid of. And this is something that we have already entered the clinic. We have preclinical data that shows that this blood can clear HIV so effectively that it is better than antiretroviral therapy. You can dump as much HIV in there and latently infected cells as you want, and it just clears itself. We were so impressed by that data, we showed it to NIAID, Tony Fauci's organization, the National Institute of Allergies and Infectious Disease, and they were so impressed, they asked us if they could repeat our experiment in their lab on their own patients, and they did. They got blood product that had the same clearance capability. You can read the article that they wrote in Molecular Therapy. So I'm feeling very confident that we have a cure for HIV here. And we just got blood last month from our first patient, and we'll reinfuse them in January. So you may be hearing safety data as early as February, and I believe we have a really good probability of next summer you reading that HIV is cured. And it really just boils down to a tiny little change that we make in the DNA of HIV CD4 positive T cells that gives them the ability to fight HIV like your cold T cells fight a cold. It's pretty exciting stuff. All right. So hopefully I've excited you about sort of the future of medicine. Let me tell you that if you're in biology, if you're in biotechnology, if you're a molecular biologist, you are the software programmers for the computer revolution for the next 100 years. If you were born in, the 50s and you started programming in the 60s, you could still find a job programming today. Digital computers, that's the kind of job security you have. This revolution, writing software for the human computer, this has 100 years in it easy. And how much value can we unlock? Well, Goldman Sachs says this industry will be $5 trillion. Okay, $5 trillion. The whole pharmaceutical industry is only $1 trillion a year. The entire computer industry is only $3.5 trillion per year. That includes everything: computers, software, smart speakers, cell phones, everything on the internet, Facebook, all that stuff. So, this is huge. You could not be in a better place. The demand for what you do will just keep going up and up and up. And if you have a sense for this future, you can pick something that not only will give you job security and a good income, but maybe something that you find fulfilling, right? One of the things that I love about working at AGT is that I'm doing something that I really care about, lifting up humankind, right? Even in this crazy world that we all live in right now, I get to do something that I know is really positive to make the world a better place. Get rid of HIV, get rid of cancer. HIV, by the way, is just a chronic viral infection. We can actually use that same process to get rid of any chronic viral infection. Hepatitis B, human papillomavirus, herpes, Epstein-Barr, CMV. There's a disease called HTLV that there's 20 million people infected in the Far East, and 1 in 20 of them will get an incurable T-cell lymphoma in their 60s. They're ticking time bombs. We could deliver 2 million doses and save 1 million lives. I mean, how exciting, right? So anyway, this is the future of pharmaceuticals. This is the future of biotech. This is an economic boom that's happening right here in the United States. It's happening other places in the world, but guess where the epicenter of it is? It's really San Francisco, Boston, San Diego, Maryland. These are the top gene and cell therapy centers in the world. And it's just endless, all the value that we'll be able to create. And our concept is we've developed a whole bunch of reusable components that you can mix and match to cure a myriad of diseases. What does that sound like? Sounds like an operating system. Sounds like an iPhone for curing diseases, right? You just write an app on top of all this functionality that we give you, and you just add a little bit of creativity, a little bit of understanding of the disease, and you could cure a disease. Some of you might even be entrepreneurs who somehow pulled together $100,000, because I think that's roughly what it would cost to get it through mouse experiments and show that it's got a good shot at working in the clinic, right? This could be the next type of garage startup, right? Instead of becoming buying $100,000 worth of computers and writing a software application, you go ahead and you get a cell culture hood and a PCR machine, and you're off to the races, an incubator, and you're off to the races. So I just think it's a really amazing time. I personally feel that people of your age are the critical driver of the future for all of us, right? You're the ones who are young enough, who are idealistic enough, that have the energy and that have the time to make the big changes in the world that we will all enjoy, right? This past this month, many of you got out there and you drove a critical change in Washington, right? You said enough, and you exercised that power to make that change, and you believed that you could do it, and you took the time, and it meant enough to you because you have to live in this world. I'll be dead before a lot of the United States is covered by water, right? But you won't. I'm on your side in all this stuff, and I'm telling you, I'm just as passionate about all these social problems and, and good government and collaborating around the world to solve the world's problems. And I get it, right? But, you guys don't just get it. You've got, the time, and you're not jaded like most of my contemporaries. Because one of the problems that you have in life is that you get knocked down enough and you get injured enough and you start to just play it safe, right? I remember when I first realized that I was mortal. I had a skiing accident where I hurt my back. It was the first time I realized that I could have a serious injury, right? But this is how we grow up, right? You haven't had a crappy boss yet, right? You haven't had somebody stab you in the back and cheat you, right? You haven't caught a horrible disease. You haven't, had to deal with a mortgage or a bank that, a predatory lender, right? You're not jaded on the world, and the world doesn't have to be that way if we insist that it's not. It has to do with respect and empathy for one another. And then it has to do with communicating, collaborating, and compromising to find good solutions that we can all live with, that lift us all up and allow the incredible diverse set of people that are out there in the world and that populate the United States to all find peace of mind, security, survival, love, right? I mean, these are the necessities in life, right? The American dream isn't that we can all be rich. Who cares about that crap, right? Rich people aren't any happier than poor people. Poor people are unhappy if they can't survive. Rich people are unhappy when their private jet is in the shop, right? Everybody has problems, right? That's the point. A lot of these people that we put up on a pedestal, and for some reason we think that addiction is bad, but being addicted to money is good. So your Fortune 500 cover, or for whatever it is, you're the Fortune magazine cover because you're the richest person in the world, or the 100th richest person, or the 50th richest person. The point is that these people aren't getting joy from that. They're actually feeling insecure instead of secure. Why? Because they've gotten to a point where they feel like they need all that crap. They don't really need all that crap. You can want whatever you want. But once your needs are covered, everything above that can be an opportunity for joy, right? So anyway, hopefully we can power this revolution, and we can start knocking out a lot of diseases that are causing a lot of suffering out there. That's the AGT mission, to leverage the power of gene and cell therapy to reduce suffering and reduce death from serious human diseases. And then we can use that as a model where we can collaborate to take on other big problems, right? We've failed at COVID in the United States, but it's taught us an important lesson, right? We can't go it alone. We can't just be selfish and ignore the facts and ignore science and wish everything away, right? No, we literally have to come together, set a strategy, tactics, a plan, and then we can do anything. We're going to cure HIV. I hope when you read about that, you're going to go, damn, he wasn't kidding, right? You can already look on clinicaltrials.gov. You can see our clinical trial. I'm just telling you like it is. So, but that shows you that even a small group of people can change the world. Have you guys heard the Margaret Mead quote? Yeah, never doubt a small group of people's ability to change the world. It's seldom anyone else that does, right? Humans can have this amazing ability to convey ideas, to make commitments that are not just intellectual, but are emotional as well. And that means that we can collaborate in huge, huge groups to move mountains. So global warming will fall if we all work together. And anyway, that's the end of my lecture. And I'm more than happy to hang around and answer some questions if you have any about anything. It doesn't have to be about gene and cell therapy. It can be about the working world. It can be about anything that you're interested in. Fire away.
Thank you so much for that amazing lecture. I definitely gained a lot of insight, and I'm sure that a lot of our club members did too. But yeah, so if anyone wants to stick around for questions, definitely do so. If you don't have any questions, good luck with midterms, everyone. I hope everyone's doing well, and I hope.
Oh my gosh, you guys came out before midterms to listen to this? Thank you. And look how many people hung on to the end. I really appreciate that. That's great. That's really great. But yeah, if you guys have to cut out, I won't be offended, so don't feel bad about it.
Yeah, so feel free to leave if you need to go study or have dinner or whatever. But if you have any questions, feel free to stick around. And yeah, thank you all for coming.